Imagine standing beside a bridge moments before giant machines erase decades of history in only a few breathtaking hours. One powerful machine can crush concrete weighing hundreds of tons, but every movement follows an incredibly precise engineering plan. You hear steel groan, concrete crack, and hydraulic pumps roar as thousands of carefully calculated forces suddenly come alive. Most people think demolition means destruction, but engineers actually see one of construction's most carefully controlled operations. Most people think demolition means destruction, but engineers actually see one of construction's most carefully controlled operations. Every bolt removed, every support weakened, and every machine positioned happens in a sequence designed months before demolition day. Think about this. One mistake could send thousands of tons crashing where crews never intended them to fall. But here's what nobody tells you. The biggest machines often arrive only after invisible preparation already transformed the entire bridge. Only after passing every demanding test does the machine receive approval to tackle real bridges across the world. But how many of these engineering giants exist worldwide? And which nations build the most? That's coming next. What decides which method engineers choose? The answer depends on science, location, and surprisingly powerful demolition machines waiting ahead. Before these machines ever touch a bridge, their journey begins deep beneath Earth's surface in enormous open-pit iron ore mines. Australia supplies nearly 35% of the world's iron ore, feeding steel mills thousands of kilometers away. Brazil follows closely, producing exceptionally high-grade or containing more than 65% pure iron for premium structural steel. The ore travels hundreds or even thousands of kilometers by train before reaching enormous blast furnace steel plants. Inside the furnace, temperatures climb above 1,538 degrees Celsius, turning solid iron into glowing liquid metal. Powerful alloying elements like chromium, nickel, and manganese transform ordinary steel into incredibly durable demolition machine components. Hydraulic cylinders demand another remarkable material. High-strength seamless steel tubes capable of surviving extreme internal pressure every single day. Those cylinders routinely operate above 350 bar, delivering crushing forces that rival the weight of entire buildings. Rubber seals begin as synthetic polymers refined from petroleum before becoming leak-proof barriers inside every hydraulic system. Copper mined in countries like Chile becomes electrical wiring that powers sensors, computers, cameras, and intelligent control systems. Heavy cast components often weigh more than 15 tons before precision machining transforms them into perfectly balanced machine frames. Most people never think about this, but every finished excavator contains materials gathered from nearly every continent on Earth. Moving these enormous components requires specialized ships, heavy-haul trucks, and rail cars engineered specifically for oversized industrial cargo. Producing one giant demolition machine also creates significant carbon emissions, pushing manufacturers toward cleaner fuels and recycled steel. And this is where it gets truly extraordinary. Next, those raw materials become the world's most powerful bridge demolition machines. Now the real transformation begins as massive steel plates enter automated cutting lines with sparks exploding in every direction. Computer-controlled plasma torches reach nearly 20,000 degrees Celsius, slicing 80mm steel with astonishing precision in just minutes. Powerful hydraulic presses then bend those glowing components using thousands of tons of force into perfectly engineered shapes. Industrial robots weld continuously for hours, producing seams that stretch hundreds of meters across every giant machine frame. Each welding arc burns hotter than 6,000 degrees Celsius, while shielding gas protects molten steel from atmospheric contamination. Experienced welders still inspect critical joints because even advanced robots cannot replace decades of trained human judgment. Next, enormous CNC machining centers remove millimeters of steel until every surface matches microscopic engineering tolerances. Spindles rotate up to 3,000 RPM as precision cutters carve perfectly flat mounting surfaces within fractions of a millimeter. Workers install hydraulic cylinders capable of producing crushing forces exceeding several hundred tons during demanding demolition operations. Hydraulic oil fills the system under carefully controlled conditions before pressure gradually increases beyond 350 bar. Powerful diesel engines delivering more than 500 horsepower slide carefully into the completed steel chassis with millimeter precision. Miles of electrical wiring connect sensors, cameras, joysticks, GPS receivers, and intelligent onboard computers into one coordinated system. Finally, the towering demolition boom joins the machine, creating a reach exceeding 40 meters above the ground. Everything is ready, but one unanswered question remains. Can this incredible machine survive the brutal tests waiting just ahead? Before this machine ever reaches a demolition site, engineers challenge every system with relentless tests designed to expose hidden weaknesses. Thousands of sensors instantly monitor hydraulic pressure, engine temperature, vibration, fuel flow, and structural stress during every movement. Artificial intelligence compares millions of measurements every second, searching for patterns invisible to even experienced technicians. High-resolution laser scanners inspect every critical surface with accuracy measured in tiny fractions of a single millimeter. Some mounting points must remain within just 0.2 millimeters, or engineers reject the entire assembly. Ultrasonic testing sends high-frequency sound waves through thick steel, revealing cracks completely hidden beneath the surface. Hydraulic systems endure pressure cycles above 350 bar thousands of times before manufacturers approve them for service. Massive vibration rigs shake entire machines for days, simulating years of punishment from the toughest demolition projects imaginable. What happens next surprised even experienced engineers when overloaded components refuse to fail under extraordinary testing conditions. Even so, about 2 to 5% of manufactured components never pass inspection and return for rework or recycling. Manufacturers follow internationally recognized quality systems, including ISO 9001, ensuring consistent production and documented inspection at every stage. Yet one final inspection still depends on experienced human eyes noticing details that computers occasionally overlook.